So last section we're going to look at this week is 4.2. This is on rational functions. And yesterday we talked a little bit about some applications. We looked at the mixture problem. We talked about what the domain is, everything that doesn't make denominator 0. Today we're going to look on what do these things look like when you draw them. We've drawn them a little bit, like when we did a concentration problem. You saw the graph of that. But we're going to look at other things besides just concentration problems, just a general rational function and how do you draw it. They're a little bit more complicated to draw than like just a line or a parabola because of the asymptotes. So we talked about two types of asymptotes yesterday. Can someone remind me what one type was? Yeah? Vertical. And what about the other type? Yep.
Horizontal.
Horizontal. Those asymptotes are going to be important when we draw a picture. So let's see how we do it. So this is something that I mentioned yesterday. You don't have to write it again. But the idea is you always get a vertical asymptote where the denominator is 0, as long as there are no common factors. So if you had something like this, what values are you not allowed to use for x there? You can't use the number 2 and, which one? 4, correct. You can't use 2 and you can't use 4. Those are the two values you can't use that are not in the domain. Now, which one of those is a vertical asymptote? There's only one of them in this case. Is it the 2 or is it the 4? Okay. Why do you say the 2? Anyone else have a thought? So first of all, do we have a common factor in the top and in the bottom? Yeah. What is the common factor? X minus 2. Okay, that's the common factor. If you have a common factor in the top and in the bottom, that's when you get a hole in the graph. So at 2, you're not going to notice anything on the graph. It's just going to be a very, very small hole. And you can keep zooming in. You'll never see it. The only way you know it's there is if you look at this equation. So the only vertical asymptote in that problem is 4. That's it. Just the 4. So asking you what the vertical asymptotes are and asking you what the domain is are two different questions. Is there any question on the difference in this problem? Okay. So let's try just graphing that. X minus 1 divided by x minus 1. Okay, so first question, what value are you not allowed to use for x? Sky? Yeah, you can't use 1. And at the number 1, is it going to be a hole or is it going to be an asymptote? It's going to be a hole. So when we graph it, let's watch what happens. It's x minus 1 divided by x minus 1. Essentially, you're dividing two things that are the same. And what do you get when you divide two things that are the same? Yeah? You get the number 1. So this is basically going to look like the graph. Let me do zoom 6. It's basically going to look like the graph y equals 1. And if all I did was show you that picture, you'd probably say that. You'd say, oh yeah, that's the graph of y equals 1. Not quite. There's a hole in that graph. And the way you would show the hole at 1 is like that. There should be the calculator can't do this, but there should be a circle showing there's a hole right there. That's what that graph looks like. Now, question? No, it's when x equals 1, because that's the value you are not allowed to use. So it's when x is 1. Now, if I go like this, what value am I not allowed to use for x now? Still can't use 1. Still can't use 1 for x. But is there a common factor in the numerator and the denominator now? No, we just eliminated the common factor. So at 1, you're not going to get a whole anymore. What are you going to get this time? You're going to get a vertical asymptote. It's going to look completely different from the last one. Just by changing the denominator or the numerator from -1 to -2. Totally changes how it looks. Kind of looks the same on the ends, like it's like a flat line over on the left and a flat line on the right. But in the middle, it's totally different. Okay, how about this one? What value are you not allowed to use for x and now? Austin? Right? You can't use 1. Now, do we have a common factor in the top and in the bottom? What do you think, Curtis? What do you think? Do we have a common factor in the top and in the bottom? So how would you write this top out? Like, what does x minus 1 to the second power mean?
It's x squared plus 1.
So like, in general, if you raise anything to the second power, what does it mean to raise something to the second power?
Multiply by itself.
So can you write this saying exactly what you just said?
No, you do x minus 1 and then x minus 1.
So that means you have 2 of them. So do we have a common factor in the numerator and the denominator? We do. It's x minus 1. We have 2 copies of it up here. We have 1 copy down here, but they both have one copy in common. So we said you can't use 1. Is there going to be a hole in the graph at 1? Or is there going to be a vertical asymptote? How about Tony? What do you think? A hole or an asymptote?
Hole.
Right, it's a hole. There's nothing to figure out there. It's very like, if you have a common factor, it's a hole. If you don't, it's an asymptote. It's one or the other. So in this case, you would have a hole. That type of hole also has another name. It's called a discontinuity, because a discontinuity is like a gap. It's a place where if you were trying to sketch your graph, you would have to pick up your pencil, put it back down, and then keep sketching. So you have your graph, and then all of a sudden you have a hole. So you have to pick it up, put it back down, and keep sketching. Now, the amount that you pick it up and put it back down is extremely small. It's infinitely small. That's why you cannot see a hole on the calculator, no matter how much you zoom in. The only way you know a hole is there is if somebody gives you an equation to look at. So that specifically, a hole is called a removable discontinuity. They call it removable because it's really infinitely small. So you might think, well, then is it really there? Yes, it is there. It's as small of a gap as you can possibly imagine, but there is a gap. And to exaggerate it, a lot of times what we do is we just put a big circle there so people notice. If you don't circle it, I wouldn't see it. So any questions on the idea of what a hole is, or more formally, a removable discontinuity? All right, so Cameron, if I have common factors in a numerator and denominator, will that give me wholes or vertical asymptotes? Wholes. Yep. Good. Okay, so this just represents, you don't, I guess you really don't have to write that, but this just represents two polynomials. Here's an example. You've got some type of polynomial in the top. You've got some type of polynomial in the bottom. I don't know how many terms it's going to have, but when we write it, we'll start with the highest exponent. The next one will go down 1, then down 1 again, down 1, keep going down 1, till finally the last number is just a constant without any letter. The x is gone. And the same thing for the one in the bottom. It's going to start with the highest exponent, then the exponent drops down 1, keeps dropping down, dropping down, dropping down, until finally you end up with just a constant. Again, there is an example. There's another example. So polynomial on the top, polynomial on the bottom. What we're going to look at is something called the end behavior model. When you look at this polynomial, look at the one in the top here. 2x squared. 2x squared minus 1. Which term here do you think is going to have more of an effect on how this looks? The 2x squared or the minus 1? Tell me. The 2x squared. Because think if x was 1,000. 1,000 squared times 2. Huge number. 1? Barely anything. So 2x squared is the most important term in the top. Now let's look at the bottom. 3x cubed plus 2x plus 1. Which term out of those three do you think is the most powerful term in the bottom? The term that's going to really control what's going to happen. Yeah? Right, the 3x cubed. And if you say, well, yeah, but if x is 100 and you multiply it by 2, that's 200. Isn't adding 200 a pretty big number? Not really. If you plug 100 in for 3x cubed, you would have 3 times 100 cubed. That's 3 million. What's adding 200 compared to 3 million? It's almost nothing. So this is the term that's going to control what happens in the bottom. This is the term that's going to control what happens in the top. Nothing else really matters. You might say, well, does it do anything? Yeah, it affects little details. But overall, those two terms are the most important ones. And those are what we call an end behavior model. Usually, the end behavior model is the very first term. Here it's the 2x squared. Here it was the 3x cubed. So in the top, this is the EBM. It's called the end behavior model. In the bottom, that's the end behavior model. Well, what we're going to do is just put the two together. So you've got an end behavior model for the top. You've got an end behavior model for the bottom. If you divide the two of them, you get the end behavior model for the whole thing. Not just the top, not just the bottom, but the whole thing. So this stands for end behavior model. And the EBM is what controls what's going to happen. It controls what will happen. Does it control every little detail? No. But overall, it controls what's going to happen. So take the term in the top with the highest exponent. Take the term in the bottom with the highest exponent. And divide them. when you divide two things with the same base, what do you do with your exponents? Yeah, you subtract them. So if you wanted to divide these two things, you'd take whatever number is in front, divide the two numbers, and then subtract your exponents. N minus M. And that is the EDM for a rational function. What does it really mean? It's like a simplified version of a more complicated fraction. It simplifies it. Takes out all the little details and said, all right, you want the big picture of what this is going to look like? This is what's going to happen. So let's try that on the next example. We've kind of already worked through it a little bit by circling some of the things, but let's see what happens. Sam, what's the EDM for the top?
2x squared.
2x squared. And Grady, what's the EDM for the bottom?
3x cubed.
3x cubed. And if you get stuck and you can't remember, like, wait, what am I supposed to do with the exponents? Just write that out the way I asked Curtis to a minute ago. This means 2 times x times x. This means 3 times x times x times x. Hopefully you don't have to write it out like this every time, but this will help you to see what's going to happen. What do the top and the bottom both have in common? Yeah? 2 x's. 2 x's here, 2 x's there. So basically, what am I left with? Oh, Fira, what am I left with?
Oh, 2 over 3x.
2 over 3x. What she just said, 2 over 3x, that is called the EDM. It's the end behavior model. It's a more simplified version of this that takes out all the details and basically says, you know what this looks like? That's basically what that looks like. Now, what we use the EDM for is to find horizontal asymptotes. The original is more complicated to look at. It's got a lot of stuff in it. The EDM is simplified. To figure out what your horizontal asymptote is, let x approach infinity or negative infinity. And tell me what happens to this fraction. As x approaches infinity, what happens to the part that I just circled? As x gets bigger and bigger, what happens to the denominator of that fraction? How about Kian? What happens to the denominator of that fraction? Well, as x approaches infinity, what's happening to the bottom? What's in the bottom? 3x. And as x gets bigger and bigger and bigger, what happens to 3x? It keeps getting bigger. So the bottom of the fraction keeps getting bigger, which means the entire fraction is getting smaller. Smaller and smaller and smaller, and it's approaching, but it will never reach what number? It'll never reach 0. And for horizontal asymptote, what letter do we use? Y. Why won't this fraction ever be 0, no matter how big you make x? Why not? What if I make x like 20 billion? Won't it be 0? Yeah?
Because 1 over like anything doesn't make it equal 0.
Yeah, in this case it's 2 over something, but if you take 2 and you divide by the largest possible number you can think of, it's still not 0. It still is small, but it's not 0. So that's what we use the end behavior model to figure out. Horizontal asymptotes. let's try this one. So we have polynomial on the top, another polynomial at the bottom. And they want us to find the EDM and the horizontal asymptote. Order you want to do it in, find the EDM first, then find the horizontal asymptote. Because think about trying to find the horizontal asymptote first here. Think about how hard that would be. Let x be a really, really big number. Now you have to imagine what would happen to the top and the bottom if you let x get really big. But there's so many x's, it's kind of confusing. So we're going to eliminate the ones that don't really have an effect on the problem and just focus on the ones that do. Okay. So Jenna, what's that EDM in the top?
Is it
In the top, so we don't have a 3x in the top.
or 3x squared?
I think there's a term there that's going to have even bigger results than 3x squared. 2x to the fourth. If you let x equal 10, 10 squared is 100, times 3 is 300. If you let x equal 10 here, 10 to the fourth is 10,000 times 2 is 20,000. 20,000 compared to 300 is nothing. So the x to the fourth term is what's going to control it. So that's the numerator of our EDM. And what about the EDM of the bottom? Yep.
3x.
3x to the fourth. Now you can write all the x's out if you want individually. But what does that reduce to? 2x to the fourth over 3x to the fourth. It's just 2/3. That's the EDM. This time there's no letter. That's okay. So where's the x then in this 2/3? There isn't one. So now here's my question. To find the horizontal asymptote, you let x get bigger and bigger and bigger in that fraction. What happens to this fraction as x gets bigger and bigger and bigger? Yep. Well, if there was an x in the bottom, it would get smaller, but there's no x in the bottom. It just stays the same. As x gets bigger and bigger and bigger and bigger, it has no effect on this number. So the horizontal asymptote is, what letter? Y equals 2/3. Okay. We're focusing today on the problems where the exponent in the bottom is bigger than the one in the top, or the exponents are the same. We are not looking at the case where the top is bigger. That gets more complicated. That's tomorrow. Okay, but we're looking at the case where the bottom is bigger, or they are the same. And that's the type of the graphs we're going to look at right now, where the bottom is always less than the top, or the bottom is equal to the top. It's like the last two problems we just did. Okay, so a few steps to sketching one of these graphs. Okay, we'll try, I think I have 2 sketches, and then that'll be it. So one thing we want to find, if we can, are the intercepts. Intercepts are an important thing that help you sketch something. Where does it cross the x-axis? Where does it cross the y-axis? Some people mix this up. To find the x-intercepts, you plug 0 in for the y value. To find the y-intercepts, you plug 0 in for the x value. So you just plug in 0, and that'll tell you your intercepts. Now, not every graph has an x-intercept. Not every graph has a y-intercept. Something like this. This was a graph we looked at yesterday. That graph does not have any intercepts. It never crosses the x, and it never crosses the y. So if you go to try to find your intercepts and it doesn't work, that's okay. Just skip it and go to the next thing. Find your vertical asymptotes. So vertical asymptotes are where the denominator equals 0. How do you do them? You factor. If you can't factor, quadratic formula, just like in last night's one. Yep.
Can you just go back for a second?
So we're going to find the vertical asymptotes. We're going to put those in as dotted lines. Then we're going to find the horizontal asymptote. Well, how do you get the horizontal asymptote if you have something really complicated? You simplify it. You use the EBM. The EBM will give you a nice, simple fraction to find the horizontal asymptote for. And that's what we just did in the last two problems. So at this point, you're going to know your vertical asymptotes. You're going to know your horizontal asymptotes. This is where the graphing calculator comes in. I know that if a value is not in the domain, I can't use it. Like if 2 is not in the domain, I can't plug in 2. But I can plug in something near 2. I could use my calculator and plug in like 1.9. Or even closer, 1.99. So once we know our vertical asymptotes, we want to check what's happening when you get close to it. I know what's happening when you're right on it. It's undefined. But what happens is you get closer and closer and closer. That's going to give us a good picture of our graph. Okay, and if you want, once you get your sketch, you can always confirm it with a graphing calculator and see if you did it right. Those are basically the 4 steps to drawing a rational function. But we're going to do 2 examples right now. This side. Does everybody have steps 1 through 4? So let's try a switch. I want to draw a picture of that graph. And if you don't follow these steps, it's just like overwhelming. It's like, well, how do I even know what to do? Follow the steps. So the graph is x minus 1 over x squared minus x minus 6. Now, I know I'm going to need to figure out the zeros of the bottom. So I might as well just factor the bottom right away, if I can. Let's see if we can do it. When I start to factor the bottom, does anybody see what the first term would be in each parenthesis? Yep. It'd be an x. How about my signs? 2 pluses, 2 minuses, or 1 of each? Yep. It is 1 of each. I'm not going to give you one that wouldn't factor here because it would make this problem annoyingly long. Longer than it's going to take. And now 2 numbers that multiply to give me 6. 2 and 3, and I would do them in that order. Let's check it. X squared minus 3x. 2 times x is plus 2x. Negative 3 plus 2 is negative 1. Perfect. Okay. Let's say you have to factor it right now, but you're going to have to factor it now or later. So now we got that out of the way. So now, let's go through. Find the x and the y intercepts. Okay, let's try to find the x-intercept first. The x-intercept is when you plug in what number for what letter. Yep, Tony.
When you plug in 0 for y.
When you plug in 0 for y. And if you're like, wait a minute, there's no y there. Yeah, yes. This whole thing is y. Half of x. So pretend like you change that to 0. You would have 0 equals, and then you'd have the rest of this fraction on the other side. What's the only way that a fraction can ever equal 0? What would have to happen for a fraction to equal 0? Yes. No, if you divide by 0, it's undefined. What can you do for division that always comes out to 0? Yep.
And the top equals 0.
Have the top equal 0. So the way that you can set a fraction equal to 0, which is what we have to do because the y is over by itself right here. For this fraction to equal 0, the top has to equal 0. Don't worry about the bottom, just the top. So what would be the x-intercept? 1. So this graph crosses the x-axis at 1. Is that enough to graph it? No, we need a lot more. But at least we have that. Okay, so we got the x-intercept. Let's do the y-intercept. What number do you plug in to find the y-intercept? Plug in 0 again. For which letter? So that's the difference. So let x equal 0. If you plug 0 into the top, what's 0 minus 1? So we get negative 1 over. Doesn't matter which one of these you use. Just use this one. What's 0 squared? Minus 0? Minus 6. Negative 6. So your y-intercept is 1/6. So it's just barely positive. Maybe about like that. That wasn't bad. I mean, it's a couple points we got, but we need a few more things. So now, let's find the vertical asymptotes. This is where we just save time, because we already did the factoring. First of all, any common factors between the top and the bottom? No, they're all different. So we are going to get 2 vertical asymptotes. What would you plug in for x to make the denominator 0? Two values. Negative 2 and 3. So we can write them down, but what's more important is we put them on the graph. X equals negative 2, x equals positive 3. Those are your vertical asymptotes. So what I'm going to do, just so I can see it easier, I'm just going to make it smaller for a second. Negative 2, positive 3, I'll fix that. Negative 2, positive 3, good. Okay, so we got that. After we find the verticals, what do we want to find after the vertical asymptote? We want to find the horizontal. And what do we have to use to get the horizontal? The EBM. Yep, we find the EBM. Okay, let's find the EBM. Okay, Gavin, what's the EBM of what's in the top?
Sorry, which one?
The top. So think of what are the two, there's 2 terms in the top. Can you tell me what each term is?
X and negative 1.
X and negative 1. Which one is going to really start to control what happens as x gets bigger and bigger?
Negative 1.
So look at those two terms. If I say let x be 1,000, then this first one turns into 1,000, and this second one is going to stay -1 all the time. This x is what's going to control everything that's going to happen, because it's going to get bigger and bigger and bigger, and this -1 is basically nothing. It's just -1, which gets to be insignificant as x gets to be in the millions. So the EBM of the top is x. Now to find the EBM of the bottom, it's actually better to go back to the way they gave you the problem. Factoring helps for the vertical asymptotes. It does not help for the EBM. You want it like that to see the EBM. So what's the EBM of what's in the bottom? X squared. And that would simplify to 1 over x. So now, the horizontal asymptote is what happens in this fraction as x gets bigger and bigger and bigger. What happens to that fraction? Smaller and smaller, and it approaches but never reaches what number? 0. There's your horizontal asymptote. So let's put that on here as well. So what these asymptotes are going to give you is basically guides to follow as you sketch this. We're going to be pinned into these sections. We're going to end up using 3 of them. There's 6. 1, 2, 3, 4, 5, 6. So there's 6 different sections. We will have a picture in 3 of them. And our picture is going to be trapped by those dotted lines. It's never going to cross those vertical lines. It might cross the horizontal. That happens. But it will not cross the vertical. Okay. All right. So now the last step is to use the calculator. See what happens when you get close to each asymptote. So the first thing is we need to type that in. We need, in parentheses, x minus 1 divided by, in parentheses again, x squared minus x minus 6. Now, I could do this part without a calculator, but calculator is going to speed it up. That's why I'm using it. What were my 2 vertical asymptotes? Yep.
-2 and 3.
Okay, let's start with the -2. What I want to do is basically plug in a number that's very close to -2 and see what happens in this equation. I can't do -2. Watch what happens if you try. Press second, press second, and then press graph. If you have any numbers there, you can get rid of them or you can just leave them. Doesn't matter. But if I try to type -2 in, it says error. Can somebody give me a number that's just a little bit smaller than -2, but really, really close to it? So a little bit more negative than -2. Yeah? Even closer. What's even closer than that? She said -2.1. There's infinitely many numbers between -2 and -2.1. Pick one closer to -2. Yeah, like -2.01. So let's plug in -2.01. That's just to the left of -2. And let's see what happens. When I plug in -2.01, I'm at -60 on my graph. That's pretty far down. If you did it even closer, -2.001, now you're at -600. So when you are just to the left of -2, your graph is way down at -infinity. So that means when we are just to the left, this is the -2, the graph is way down there. Now, let's try when we go just to the right of -2. So can somebody give me a number that's just a little bigger than negative 2?
Negative 1.99.
Sure, negative 1.99, 999, that's fine. When I plug that in, all of a sudden my graph is up at positive 600. Basically, it's way up. So when I go just a little bigger than negative 2, I'm way up there. All right? Let's do it again. Now let's do it for 3. So I don't want to type in 3 because that's an error. But what's a number just a little smaller than 3? Jen? Sure. Let's go even closer. 2.999. Really, really, really close. At 2.99999, I'm at negative 400. So when I'm smaller than 3, I'm way down there. I mean, that's not even close to negative 400, but that's the best I can do. And let's check what happens just to the right. What's a number a little bigger than 3? Oh, Chris?
What was the question?
A little bigger than 3.
A little bigger than 3. 3.001.
All right, so 3.001. If I go just after the number 3 on the x-axis, I'm up at 400 on the y-axis. So I'm way up here. So at this point, we have enough information to make our sketch. Let's look at the middle. That's the easiest part to see. It has to go through all 4 of those black dots. And it has to stay as close as it can to the vertical asymptotes. So it's going to start like this. But then it has to start curving because it's going to go through those 2 in the middle. So it's going to curve. But it can't keep going straight because it hits another wall. So, but it has to go through this dot down here. So it tries to keep going straight, but it's forced to go down through this point. So it's going to go something like that. And it's just going to keep getting closer and closer to that vertical asymptote. So that's what happens in the middle. That's the middle section. On this one, we know that it's going to stay very, very close to that asymptote for as long as it can. But it can't keep going up because it hits a wall. So what does it have to do? It tries to keep going up, but that wall kind of deflects it. And it forces it to continue that way. And the same idea is going to happen in the upper right. It has to stay very close to this vertical for as long as it can. But then all of a sudden, it starts to see a wall coming up in front of it. So it can't hit the wall. So it has to kind of turn to avoid it. And it comes down. And it looks like that. And that's generally pretty much what all those look like. They have those 3 sections just like that. Let's hit graph and see how we did. I might not have my curve perfect, but it's pretty close. It was actually a little bit flatter in here than I did, but that's fine. Yeah.
May I use your question?
Yeah. Okay. Any questions on? Okay, try one more of the same thing, and that's it. So what's the first thing I should do to the bottom? Because it's going to save me some time later if I get this done now. Factoring. This isn't the more complicated factoring because it doesn't have 3 terms. It only has 2. So all you can do is factor out the GCF. What is the GCF of the bottom? What is it? Just x. So all we can do is factor out an x. And if I factor out an x, Austin, what will that leave me with in the parentheses?
2
Mhm.
minus 5.
2, we need something else.
Oh, 2 squared.
2x
Minus 5.
minus 5. And the numerator, it just stays the same, so I'm not even going to write it again. Okay, vertical asymptotes. Alex, when I write my vertical asymptotes, how does the equation start? X equals, right? And then for horizontal, it's y equals. Okay. What could you plug into the bottom to make that 0? Yep. 0. That's this part. How about this part? I prefer it as a decimal because that's easier for me when I need to graph. Chris?
2.5.
2.5. Yep. 2.5. Okay, so there's my verticals. I'll graph those when I'm ready. My horizontals. Well, let's find the EDM first. Okay, 1. What's the EDM of the top?
3x squared.
Yep. And how about the bottom?
2x squared.
2x squared. And what does that reduce to? 3 over 2. So now, can somebody tell me what happens to 3 over 2 as you let x get bigger and bigger? Nothing. So it stays as 3 over 2. There's your horizontals. There's your verticals. Now we're ready to sketch them and then use the calculator to finish it up. All right. So let's do x equals 0. And x equals, what was the other one? 2.5. About right there. And the horizontal? 3 over 2, that's 1.5. Let's fix that a little bit. Close enough. Now, they also mentioned the x-intercept. Well, I'm not worried about the x-intercept here because that means we have to set this equal to 0. That's just going to be a mess. And it's only going to be one single point, so how much is that really going to help us out? I do want to look at the y-intercept though. Yep. Yeah. What's the y-intercept is when you plug in 0 for what letter? X. But what did we already say about 0 earlier? Yeah?
It can't be plugged into x.
In what?
It can't be plugged into x.
Why?
Because you would have to divide by 0.
Right. To find the y-intercept, you need to plug in 0 for x. But in this problem, you can't. If you plug in 0 for x, you're going to cause yourself to divide by 0. So what do you think that means about my y-intercept?
You don't have one.
I don't have one. This graph will never cross the y-axis. So that's what I mean by sometimes that's not helpful. All right, let's put it on the calculator so we can finish it up. Okay, the trick to always putting it in is put parentheses around the top and the bottom. You have to do that. So 3x, I said put parentheses. 3x squared plus x minus 4 and 2x squared minus 5x. So now the goal is to look at the table. If you have other numbers there, just ignore them. They don't mean anything. But we want to plug in numbers near the vertical asymptotes. Let's start with 0. What's a number that's just a little bit smaller than 0. Negative 0.001. Okay, good. Let's do them all. What's a number that's a little bigger than 0? 0.001. Okay, so I got that. What was my other vertical asymptote? Oh, Grady, what was my other one?
I don't know. 2.5.
2.5? What's a number that, I can't do 2.5. Okay, we already know that's going to be an error. So give me a number a little smaller than 2.5. Asia?
A little smaller.
Yeah. And then bigger.
2.3.
We got to go closer than that. We only,
Okay.
I mean, real
2.4.
close.
Oh, closer?
Oh yeah. I want close.
Okay, then 2.49.
Okay. So 2.499. Really close. And how about a little bigger than 2.5?
2.51.
Closer.
0.
Sure. So this is going to tell us everything we need to know about what's happening with our asymptotes. Right. So let's look at it. When we are to the left of 0, we're down at negative infinity. Way down. When we're to the right of 0, we're way up at 800. Here's 0. We're way up at 800. How about when we are to the left of 2.5? Where am I? Kim?
Say the left.
Yeah.
Yeah, sorry.
We're to the left of 2.5. Where are we?
Very far up.
I don't think so. We're to the left. That means we're a little smaller than 2.5. We're at negative 3,448. So we're way down. So here's 2.5. And when you're to the left of it, I know that's not even close to negative 3,000, but it's the best I can do. And what about when we're to the right of 2.5? Right?
High.
Way up high. So now, zoom out so you can see what's happening. Okay, you've got a graph in the lower left that has to stay close to the green line, but then all of a sudden it can't. So it's going to be deflected by that horizontal. In the middle, it has to connect these two dots, and it has to look like a curve. So it's going to kind of come down. I don't know exactly where it's going to curve, but it's probably going to do something like that. The middle is so steep this time that the calculator probably can't draw it. It's probably not going to work. And this section, it's going to look like that. Let's see what happens with the middle. I don't think the calculator is going to be able to draw it. No. It got too steep in here. So when it gets too steep, the calculator gives up and it just stops. But my graph this time is better. That's what it should look like.
Can I please have everyone's attention? The following practices have been canceled. JD Golf. Thank you.
All right, so that's the homework from the first part of 4.2 on sketching rational functions. We'll finish the last half of 4.2 tomorrow, and most likely there'll be some type of take-home for homework tomorrow night. At least partially, or maybe totally. I'm not sure. But there'll be something instead of regular homework tomorrow on Edge Elastic.